Okay, so let us recall that in the previous vector space video, we managed to show that for a finite dimensional vector space V, there exists a natural isomorphism between V and V double hat, that is the space V and its double dual or second dual. And that isomorphism actually does not depend on any chosen basis for the original space V. So in that sense, the construction of that isomorphism is a basis free construction. So let us now see what else this section has. Next, we have this definition. And that construction is in fact also called an invariant construction, which does not depend on the basis. So next we have this definition. Let V be a vector space and W be a subspace of V, any subspace. The annihilator of W is defined as this. The annihilator of W is denoted like this, A of W, and by definition it is the set of all the linear functionals in V over F. That means all elements in the dual space of or the original space V, such that the F image of every element in W is equal to 0 for all W belonging to W. Okay, so from the definition you can immediately see one thing, that whatever this A of W turns out to be, it is actually after all a subset of the dual space of V. That means the first dual. Now you can perhaps already guess that this A of W is going to be itself not just a subset of V hat, but rather a subspace of V hat. Now that can be of course shown directly. However, we are going to see something very soon. In that situation, this A of W will turn out to be the kernel of a vector space homomorphism. So being a kernel of a homomorphism, it will then automatically follow that this is a subspace. So we are not going to right now show from scratch directly that this is a subspace. We however mention this fact along with another fact. Okay, so let's see what these things are. It turns out that this is a subspace of the dual space of V hat. So that is one thing which we are just simply saying without any proof. We are going to go to that. And also there is another thing. If U is a subspace of V such that U is contained in W, then A of u, the annihilator of u, contains the annihilator of w. That is, it gets reversed. The containment relation, the direction of that thing gets, it becomes the other one. Okay, it changes. And this is actually quite easy to see. In fact, let's just see it here itself. For okay, let me just phrase it this way. Let u be contained in w. Now, what do you want to show? You want to show that this is contained in this. So let's just take one element here and then show that that element is here also. But what type of elements are there in the annihilator of w? After all, linear functionals, which, and in fact that's why it's called the annihilator of w. It's the set of those linear functionals that annihilate or eliminate w, the subspace w, completely, in this sense that whatever input you put in this function, in this linear functional from w, that is going to be annihilated. That means that is going to be made 0. So let's just take f to be any element in the annihilator of w. Then by definition of A of w, wf is equal to 0 for all w belonging to w. But now note that u is just a subset of w. So whatever we are saying here, which is true for all the elements of w, in particular they are also going to be true for all the elements of u. That is because u is just a part of w. So in particular, wf is equal to 0 for all w in u, in capital U. This implies f belongs to the annihilator of u. Hence, the annihilator of u contains the annihilator of w. So that's how we have this containment or this relation. Okay. So now we are going to see a relationship between the annihilator, the dual space of w and the dual space of v. Can we set up any function in between them, say from this to this one, which has some nice properties? Let us see, and which ultimately will somehow be related to the annihilator of w. That is our aim now. So let us see what we can do. But now, instead of taking an arbitrary vector space V, we are going to take a finite dimensional vector space V. So let us now start like this. Let V be a finite dimensional vector space and as usual WB is subspace of V. Then of course W also is going to be finite dimensional. Those things we will need later. So let us first of all try to define that function. So we are trying to define a function from the dual space of V into the dual space of W. Okay. For any element, so that means our input is going to come from here, f belonging to V hat, let f tilde be the restriction of f to the subspace W. B the restriction of f to W. What does that mean actually? You see, because f is in V hat, basically f is just actually f is just a function with domain V and taking its values in the underlying field f. The underlying field of course is always there, we need not even mention it. But now what we are saying, f tilde is the restriction of f to W. So W is a part of V because V is the entire space, W is a subspace. So we can consider the restriction of f to W. So that means we can consider the restriction function whose domain now becomes W, the restricted region, and of course the function is still f value, that is the field value function. So we however write it in detail, that is f tilde is the function from W into f such that W f tilde, where this W is coming from W of course, is by definition nothing but the f image of W. The rule for this function is just the rule for the original function f. The only thing we have changed is the domain from V to W. Now it's extremely easy to see that the nature of f as a linear transformation, that is as a vector space homomorphism, it will transfer that nature to f tilde also. Still, because we are in fact in doing all these things, we are in fact not skipping things, that is we are in fact doing as much as possible, no matter how trivial the things are. So let's just see that one also, instead of simply mentioning that f tilde is in W hat for, but before that is, you see, whenever you define a function, you have to first of all make sure that it is well defined. Is it well defined? Yes, of course it's well defined, because as a function it's just nothing but a restriction, and restriction of a function is a notion that we have already seen before in the very first preliminary chapter, where we have that section on functions. There itself we have seen that there is something called restricting a function to a subset of the domain, and that in fact gives us a well defined function. So this is well defined. So we can just simply now try to show that this is a linear transformation. for W1 and W2 belonging to W and alpha belonging to F, we see that W1 plus W2 F tilde is going to be equal to what? W1 plus W2 F by definition of F tilde. But keep in mind, we are able to write this F in place of F tilde. That's because W1 plus W2 is in fact an element in W, and that is coming from the fact that W is a subspace. So if you add two elements of W, we are again going to get an element of W. So because of that, you are able to write like this. Now you just use the fact that F respects addition. So this is W1F plus W2F. And but then again, this is nothing but W1F tilde plus W2F tilde. So that's how, just like F tilde also respects addition. And now let's look at alpha W1 F tilde. Again, because W is a subspace, so alpha W1 itself is a vector in W. So that is why this is equal to this, but because F is again a linear transformation, so you can write in place of this, and that equals alpha, W1 F tilde. So now you can of course say that F tilde is a linear functional in W, or in other words, is an element in W hat, the dual space of W. Hence, belongs to W hat. So this gives us the idea of how to define a function from V hat to W hat. Because what we have done, you see, we started out by taking an element F in V hat, and now we have got an element F tilde in W hat. And we clearly see what the relationship between F and F tilde is. F tilde is the restriction of F on W. So this will help us set up this map. So let's now do that. Now define the function t from V hat to W hat by this. Ft is by definition F tilde, and if you want to be still say more specific, you can write where F tilde is the restriction of F to W. So it's not just about the particular function F, but any function, any functional in V. About that we are for any functional F in V, we are defining the function T like this. Okay, so now our aim is to show that this T is of course well defined because our W is a fixed subset of V. So whatever functional f we choose from here, its restriction to W will be a unique function. So for a given f tilde is actually unique, and f tilde of course is there in this set. So T is well defined. Let's just simply mention that. T is well defined. Okay, now our next aim is to show that T is itself a linear transformation. That's because it's a function between two vector spaces after all. Both are vector spaces over the same field F, that same underlying field. So now so we will need two vectors from the domain space and a scalar from the field. Because we have already taken alpha, let's just use another symbol beta, and we now have to prove that T respects addition as well as multiplication by scalar. Note that, so first we see addition. Note that f plus g T is equal to what? By definition it is this. Okay, where you understand that this denotes the restriction of f plus g on W. Fine. Whereas ft plus gt is what? This is f tilde plus g tilde. Our aim is to prove that as functions, these two things are actually equal. Note one more thing, that just like what we did when we were talking about f, for T also, how are you exactly able to write this in place of this? You would say of course that by the definition of T, but the definition of T demands that the input be in V hat. Is f plus g in V hat? Yes, that's because f and g are coming from V hat, and V hat is a subspace. So that's why f plus g is also in V hat, and that's why this makes sense. And there of course you do not even have to argue like that. They are directly f and g are coming from V hat, so you have that. Okay, so now we want to prove that this function and that function are actually equal. But they are, what type of functions are they? They are functions, each one of them is a function from W into F. So let's see how they behave on a given input coming from W. For any W belonging to W, we have, so what happens when we apply this restriction on W? Because this W is after all coming from W, and this is a restriction of f plus g on W, I mean this function is, so by definition of restriction, this is W f plus g. But by the definition of addition in this space, that is by the meaning of f plus g, this is nothing but wf plus wg. In fact, this is what this symbol means. Again, using the fact that f tilde is the restriction of f on w and g tilde is the restriction of g on w, these two things can now be written like this: f tilde plus w g tilde. And now, by the definition of addition in w hat, this sum is in fact the same as this. Why did I say by the definition of addition here? That's because f tilde and g tilde are elements here and their sum has this meaning. Okay, so we are now having this. So that means these two functions have identical behavior on every element in capital W. So as functions they are equal. This shows that, let us start from here. This is equal to f tilde plus g tilde, and that is nothing but ft plus gt. Does everything make sense? Let us see. Of course, whatever we have done till this, we believe that we have not made any mistake and our logic is sound. But let us just see for once, what is this plus? This is the addition that we have in phi hat. Fine. What is this plus? This is the addition that we have in w hat. So this equation actually is telling us that T respects the addition operation in these two structures. When you transition from V hat to W hat, the addition is respected in this sense. Additions are respected, rather I should say. Okay. And now next, we already have taken one beta, and but I will not get it directly. No, just like this one, I have to carry out two things, one after another. So let me just write, and let me write also again I am writing alpha beta f t. That equals, of course, the restriction of beta f, and beta times ft is equal to beta times the restriction of f. Okay, and here also we have to show that these two functions are equal. So let's apply them on W. So for any W coming from W, we have beta f tilde. By definition, this is nothing but the W image of beta f. Now by the definition of scalar multiplication in this space V hat, this thing means beta times WF. Okay, so now, and this again of course means beta times WF tilde, because W is just coming from capital W. So WF is the meaning of WF tilde, because that's how this restriction F tilde has been defined. And now there is one more step. Now by the definition of scalar multiplication or multiplication by scalar in this space, this thing is equal to this. So that's how we get the fact that these two functions are equal. So now we can conclude just like the case for addition. Hence, beta ft, which is equal to the restriction of beta f on W, or 2W rather I should say, that is equal to beta times f tilde, which is equal to beta times ft. Okay, so we have now completed showing that T is in fact a linear transformation. So T is a, because we are still not using the term linear transformation, so let's just write homomorphism is a homomorphism of V hat into W hat. Okay, now we are going to see what the kernel of this homomorphism is. What is the kernel of T? Let's just ask that. Next, let say H be any element in the kernel of T. Don't forget that because H is in the kernel of T, H must after all be in V hat, because the kernel of T is supposed to be a subset of the domain, actually a subspace of the domain. So that's why H is in V hat. So basically H is just a linear functional in V over F. Okay. Then what does it mean for something to be in the kernel of T? Then Ht, which is by definition of T, H tilde is equal to 0. What is this 0? This 0 is the 0 element in W hat. In other words, it's the 0 function on W with with the f valued function. It's the 0 linear functional in W over F. This implies that WH tilde, which is equal to W0, this 0 is actually a function, okay, and it maps every vector onto the 0 scalar, 0 field element for all w belonging to w. If your input is coming from w, then h tilde is actually nothing but h, because although it's the restriction, so as functions h and h tilde are not the same thing, however the rules defining these two functions are identical on w. So that's why wh tilde is nothing but wh. That is wh is equal to 0 for all w belonging to w. But now recall that this is precisely the condition for h to be in the annihilator of w. Thus, h belongs to a of w. Okay, so we have proved that any kernel element is in the annihilator. So the kernel is a subset of the annihilator, but of course the converse is also true. So let's see that one also. Now, if say k belongs to a of w, then by the definition of a of w, wk is equal to 0 for all w belonging to w. Okay, I think I need ink, so just give me a moment. So now from this it will of course very easily follow that k is in fact going to be in the kernel of T. So being constantly 0 on W means what? It just simply means that the restriction of K on W is identically 0, and the restriction of K on W is K tilde for all W belonging to W. Thus, this is identically 0, that is, this is the 0 function on W taking its values in F, or but this is nothing but kt, and that is equal to 0. Hence, K is in the kernel of T. So we have also proved that any element in A of W is also in the kernel. That means A of W is also a subset of the kernel of T. So actually they are equal. Hence, the kernel of T is precisely the annihilator of W. Now you may of course make fun of me for going through so much just in order to prove that the annihilator is a subspace of V hat. Yeah, you can of course do that, but the point here is that we were anyway going to do all these things. So why prove this separately, that this is a subspace of V hat, since it's going to drop out as a consequence of all these things? Note one more thing, that although we started off by considering V to be a finite dimensional vector space, but we have so far not used that finite dimensionality up to this point. So that means whatever we did here is equally well applicable when V is not finite dimensional. So we can make a statement here, that is, we can conclude here midway of something, because our job is not over yet. We are still going to show that this T is not just a homomorphism of V hat into W hat with this kernel, but rather that is in fact also onto. Okay, and in showing that onto part, we will really need the fact that V is finite dimensional. Till this, however, we have not really needed finite dimensionality, and we don't need actually, as you can clearly see. As a consequence, A of W is a subspace of V hat. Note that this is true even when V is not finite dimensional. Okay, so this much we have done, but now let's come to the question of T being onto. We now show that T is in fact onto, it says adjective homomorphism, since V is finite dimensional, so is W, because it's a subspace of V. So that means it will have a finite basis. Let this be a basis for W. But we know from a previous result that if we have a basis for a subspace, then we can blow it to a basis for the entire space by introducing some additional vectors if necessary. Then there exist vectors. Vectors are elements, whatever you may want to call them, V1, V2, etc. up to Vr, belonging to V, such that and you can clearly see that we have already started using finite dimensionality here. such that M V1 Vr is a basis of V where M plus R is actually equal to the dimension of V. Fine. Now we know that this is the basis for W. So these vectors will span W. And these are some other additional vectors, okay, which actually do not belong to W. And that's why we are able to write that M plus R is equal to V. So if these vectors span some of course they will span some subspace, let's call it W1, then not only will V be a sum of W and W1, but it will be a direct sum of W and W1. So if W1 is the linear span, let me just write it using the notation. Linear span of these extra vectors, then V is the sum of W and W1, but it's the direct sum. And because of the directness of this sum, whenever you express any vector in V as a vector in W plus a vector in W1, that expression is unique. There is only one such expression. Okay. Now, what is our aim? So far, we have just simply used the finite dimensionality of V and hence that of W to have something like this. Now, our aim is to prove that our mapping T from V hat to W hat is onto. So that means we have to take an element here from here and show that it's the T image of something from here. So we have to now produce that something. So let us first take an element here with the help of this. Now let what can we take? F, G, H, K, I, J. Let's just take anything, say L. Let L be any element in W hat. Okay. Now for any V belonging to V, there exists. So we just we have taken L from W hat and we are just keeping it like this for the time being. And we do something else, namely we are going to now see what is the consequence of this. It's just that any element V is uniquely expressible as a sum of vectors coming from these two subspaces. So there exists unique W in W and W1 in W1 such that V is equal to W plus W1. Unique W in W and W1 in W1 such that V is equal to w plus w1. Okay. Now, keeping in mind that our aim is to find an inverse image of L under T, we now need that inverse image, and that inverse image we are now going to define like this. This is going to look weird, but let's just call it M belonging to we cannot directly write belonging to V hat. We have to show that. Define M to be a function from V into F by this rule. Vm is equal to W L. Does it make sense? You see, M is a function from V into F. So the input is going to come from V. So that input is say V. But that V is uniquely expressible like this. For a given V, there will be exactly one W in W and one W1 in W1, such that V is equal to W plus W1. So what we are defining Vm to be is this. Vm by definition is the image of W under the function L. Because L is coming from W hat, L itself is a function from W into F. So this is going to be a filled element. But is this M unique? Well defined? Yes, it is well defined. Because for a given V, first of all, you see, there are two things when you are checking well definedness. You are taking V, and then Vm by definition means WL. So WL, because of this thing, is a filled element. So for an element here, that is small v coming from here, you are getting a filled element. That means something here. Okay. So first of all, the sets make sense. And then comes the question of uniqueness. Because for a given V, W is unique. So this W is unique. But then for that W, LW is unique. That is because L itself is a well-defined function from W into F. So without of course writing all those things, we just simply mention, note that M is well defined. Okay. But we do not just simply need well definedness. We want to in fact show that M belongs to V hat, that is M itself is a linear functional. So for that, let us take something else this time. Say V and V prime belong to V, and say gamma belongs to F. Then we have W and W prime belonging to W, and W1 and W1 prime belonging to W1, such that V is equal to W plus W1 and V prime is equal to W prime plus W1 prime. These expressions are unique, we already know. We don't need the uniqueness here, however. Okay, now what is the effect of M on V plus V prime? Of course, we should first of all bring this to the proper form so that we can use the definition. You can see that this is W plus W1 plus this thing M, the M image of this. Now inside we can of course write W plus W prime plus W1 plus W1 prime. But the question is why? I mean, how are we able to write this? That's because we are, after all, in the vector space capital V, where vector addition is commutative and associative. So that's why you can write any sum in any manner. Okay, now you see that V plus V prime in fact has been expressed in this form where W plus W prime is in W and W1 plus W1 prime is in W1. Why? Because these are subspaces. So you take vectors from them, take their sum, they are going to lie in the subspaces. So V plus V prime already has been written like this, where this part lies in W. So now we can apply the definition of M and write this to be equal to the L image of this. But where is L coming from? L is coming from, do not forget that we have taken L from W hat. So that means L is a linear functional on W. So, and these things are coming from W. So L respects addition. And this thing is again by definition of M, Vm, whereas this one is V prime M. So that's how M respects addition. And this of course is not the end of the story, and now we look at multiplication by scalar. That's why we have taken gamma, and gamma V M is equal to, of course we are going to use this M, and that is equal to, now you use one of those four vector space axioms and write this as gamma W plus gamma W1, its M image. Now note that because W is coming from W and gamma is a scalar, so gamma W is in W, and also at the same time, just like that, since W1 is coming from W1 and W1 is a subspace, so gamma W1 belongs to W1. So this vector has been expressed as the sum of a vector from W and a vector from W1. So now we can apply the definition of M once again and have this. So this will be equal to gamma W M, L. Now L is a linear transformation with domain W, and this W is coming from W, so L respects multiplication by scalar. So we have this, and which is equal to gamma times V M. So we have shown that M respects both addition and scalar multiplication. Hence, now we can say that M is a linear functional on V over F. Okay, but what is its T image? Next, the T image of M is by definition what? M tilde, where M tilde is the restriction of M to W. Okay, so let's see what that restriction actually ultimately turns out to be for any W belonging to W. What is WM tilde? WM tilde by definition, since it's the restriction to W, is nothing but WM. Now, how to calculate WM? Note that according to the definition of M, to calculate the value of a vector, or rather I should say the value of M at a vector, you have to first of all know what that vector is, what its representation is as a sum of a vector in W and a vector in W1. But in this case, that representation is this. W is of course coming from W and 0 is coming from W1. So because such representations are unique due to that sum of W1 and W1 being a direct sum, so this is the only representation. So by now we can apply the definition of M and write this equal to WL. Okay, because that's what M means. Now you see that M tilde and L actually behave identically, and they are of course both functions on W. This shows that MT, which is equal to M tilde, is actually equal to L, and this is what we were trying to find. L we chose to be any element in W hat, and we were trying to find an inverse image of L under the function T, and this is one such inverse image. Thus, T is onto. So let's now summarize what we have found so far. Hence, and from this summary we are going to make our final conclusion. Hence, T is a homomorphism. Actually, it's okay. Let's just write like this itself. Homomorphism of V hat onto W hat with kernel A of W. So now from your homomorphism theorems, isomorphism theorems, whatever you want to name them, from one of them, W hat is isomorphic to the quotient space of V hat by the annihilator A of W. And from this we of course are going to get something about the dimension, and this implies what? Dimension of W is equal to the dimension of W. We already know that a finite dimensional vector space and its dual space have the same dimension, so that's why we have written this. But now from this isomorphism, this dimension is equal to this dimension, and this on the other hand from a previous result equals the dimension of V hat minus the dimension of the annihilator, and again using the fact that this dimension is equal to the dimension of the original space V, we finally get this. And now we can rearrange it a little bit to finally have this. Thus, the dimension of A of W is equal to the dimension of V minus the dimension of W. So this way we have actually calculated what the dimension of the annihilator should be in terms of the dimension of the original space and the given subspace. And this entire thing is a result, which of course we have just arrived at through this discussion. This is your theorem 432, and the theorem is just this: if V is a finite dimensional vector space and W is a subspace of V, then W hat is isomorphic to the quotient space of the dual of V by the annihilator of W, and the dimension of the annihilator equals the dimension of V minus the dimension of W. Okay, so this we have this nice theorem, and we have its proof of course also. That's how we arrived at the theorem, and here I end things. Okay, this result besides being nice and is of its own interest, but besides that it has applications in the theory of linear homogeneous equations in several variables. This result allows us to say something about how large the solution space of such a system should be. Okay, so we will see those things in the next vector space update. Now, according to the schedule, tomorrow I should have a video, and then of course day after tomorrow, and then on Tuesday. However, these 3 days I won't be able to film due to the coming Diwali festival, and you may also have some form of festival in your own community. So let me just take a small break, okay, for these 3 days. So the next upload will be on the next Friday, and so we have already again gone through the cycle, not fully of course. We have so far once again seen group theory, field theory, vector spaces. Then next Friday let's again do calculus. So that being said, this is just it for tonight. If you want to make a comment, you can of course use the comment section below, or you can mail me at my usual address. The link will be there in the description. And that's just it. I wrap things up. So see you next Friday with calculus. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice holiday. I'm out.